Hello viewers, now taking you through the story for A-Level Physics Paper 2. And this video I'm going to go through the topic of reflection of light at curved surfaces. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we start, let's first look at the course outline of this paper. So physics paper 2 is divided into four parts. The first part is geometrical optics, or what we call light, where 2 questions come from these topics. The second part is physical optics, or what we call waves, where 2 questions come from these topics. And the third part is electrostatics and electricity, where 3 questions come from these topics. And the fourth part is magnetism and alternating current, where 3 questions come from these topics. So we already finished this part of electrostatics and electricity, and now we are on the part of geometrical optics. So this first topic here has been skipped because it does not have calculations. So we shall go to the second topic, which is reflection of light at curved surfaces. Remember, on this platform we are interested in the calculations, but worked examples are available in the books which have been written, and that is Mastering A-Level Physics Paper 2. So all the topics of Physics Paper 2 are available in this book, and if you need a copy, contact the author on any of these 2 contacts. So that has been Physics Paper 2, but for a complete set of physics we need 3 books. There is Physics Paper 1, Physics Paper 2, and a Physics Topical Question Bank. Then from students of math, there is Math Paper 1, Math Paper 2, and a Topical Question Bank. Subsidiary math, it is only 1 book, and the rest are for O-Level. So now shall start our topic, reflection of light at curved surfaces. So in A-Level, curved mirrors, curved surfaces is the same as curved mirrors. And there are mainly 2 types of curved mirrors which you are interested in. They are the same mirrors you covered in O-Level. One is called a concave mirror or a converging mirror. The second one is called a convex mirror or a diverging mirror. So there are the 2 types of mirrors which we are interested in this topic. So let's first talk about a concave mirror. So a concave mirror is a type of curved mirror in which the reflecting surface is curved inwards. So let's try to illustrate that. So this is what we mean, that the curved reflecting surface is curved inwards. If it was outwards, it would become a diverging mirror. So always remember that for a concave mirror or a converging mirror, the reflecting surface is curved inwards. And this capital F is what we call the principal focus, and this is what capital C is what we call the center of curvature of the mirror, and this P is what we call the pole of the mirror, and AB is what we call the aperture of the mirror. So as I've been talking about, C is the center of curvature, P is the pole of the mirror, AB is the aperture of the mirror. And now shall say that when a narrow beam parallel to CP, which is the principal axis, and close to it, is incident on a concave mirror, it converges. So this is where the word converging mirror comes from. It converges to a point capital F, known as the principal focus of the mirror. So when you have a ray which is parallel to the mirror, it will be reflected to pass through this point capital F. You can also have another ray to also converge at that point capital F. So capital F is what we call now the principal focus. And the distance from principal focus to the pole is what we call the focal length. While the distance from the center of curvature to P is what we call the radius of curvature. So since light rays actually pass through capital F, the mirror is said to have a real focus. So this is another point to note, that concave mirrors have real foci, and this focal length is positive. So when you talk about concave mirror, remember that focal length must be positive. So that is, now we shall go to the symbols which we usually use when drawing ray diagrams for concave mirrors. So there are two types of symbols which are recommended. The first one is this. I think we see that even the curved reflecting surface is still curving inwards. Another one is when we put it at the top here. So it will be in that form. So any of these two represents a concave mirror. So we shall be using these ones frequently in our ray diagrams. Now we shall go to a convex mirror, or what we call a diverging mirror. So this is the opposite of the concave mirror, whereby the reflecting surface is curved outwards. So let's try to illustrate that. So I think you see that the reflecting surface is curving outwards. Still, P is the pole of the mirror, F is the principal focus, C is the center of curvature, and B is the aperture. So I can just repeat those ones, but we have already seen them. Then what we want is this one. That when a narrow beam parallel to CP, which is the principal axis, and close to it is incident on a concave mirror, the refracted rays appear. Remember, for concave mirror, the rays were real, actually passing through the focus, but here they just appear to come from point F, behind the mirror, known as the principal focus. So I can try to illustrate that. So when it reaches here, it will be reflected. But in this reflection, it will, like this ray which is reflected, appears to come from point F. The same applies to this other ray. Still reflected so that it appears to come from point F. Another ray still the same, appears to come from point F. Another one also, it is reflected and it appears to come from point F. So when it comes to convex mirror, the rays just appear. That is why these ones are dotted. They just appear to come from point F. Now what does that imply when it comes to calculations? So when it comes to calculations, it implies that it has a virtual focus, and therefore focal length will be negative. So each time it comes to convex mirrors, focal length has to be negative. So that should be remembered because it is going to be used in the calculations. Still, we shall do the same with the symbols, similar to the previous ones, only that here this reflecting surface curves outwards in both cases. So any of the two symbols you prefer to use is okay. Okay, so like I told you here, the theory part is to take us to the calculations. Now the calculations also require you to be able to draw ray diagrams. So we shall now see how these images are formed on curved mirrors. So the nature, position, and size of images formed by curved mirrors can be got using any two of the rays. So remember, the rays are 4, but any 2 are okay. Even in O-level, you also drew these ray diagrams. But the difference is that in O-level, you used a graph paper to draw these ray diagrams. Here we only make sketches. I repeat, in A-level, we only make sketches. So you no longer need a graph paper to draw a ray diagram for curved mirrors. And all the rays are drawn from the top of the object, which is represented by a straight line with an arrow perpendicular to the principal axis. So the principal axis is that the object will be vertical. Here I've drawn we shall see it in the actual diagram, but represented by an arrow, meaning this will be the top of the object, as we shall see when we begin drawing the ray diagrams. So like I told you, there are 2 types of curved mirrors, and each mirror, the way you draw differs. So let's start with a concave mirror. So for a concave mirror, like I told you, there are 4 rays, and we shall list all of them, then we draw. Or let's draw step by step. So this first ray says, a ray parallel and close to the principal axis passes through the principal focus F after reflection. So let's draw that ray in this slide. We shall list them as we draw so that we can easily follow. So we shall first draw our symbol for the curved mirror. Then put the principal focus and the center of curvature. Then we show the object. Okay. Then we said a ray parallel to the principal axis. This is the principal axis. This is the principal axis. A ray parallel to the principal axis is refracted so that it passes through the principal focus capital F. So let's see that reflection. So what you should realize is that each ray I'm drawing, it has an arrow, and that ray is starting from the top of the object. Okay, that is ray number 1. But remember, we said you need 2 rays. You need 2 rays for you to locate the position of the image. So shall come and get the second ray. The second one says a ray through the principal focus, capital F, is refracted parallel to the principal axis. Okay, so let's also see that. A ray through the principal focus, capital F, will be reflected parallel to the principal axis. Okay, so I think realize that here they are intersecting, and that will be the position of the object. Remember, these rays were starting from the top of the object. It means that even where they intersect is the top of the top of the image. So that are 2, but there are also other 2 more. Like I said, it is you to choose any 2. So let's say the third one. The third one says a ray through the center of curvature C is reflected along its own path. So a ray through the center of curvature will be reflected along its own path. That is why you are seeing this arrow here and another arrow coming back along the same path. And I think you realize that they all intersect at the same point. Okay, let's look at also the last ray. The last ray says a ray striking the pole at an angle theta is reflected, making the same angle theta at the pole at the point of the pole. So it means that here, from here, if it comes and meets the pole here, you'll measure this angle such that even after reflection, the angle must be the same as before. And that comes from the laws of reflection. Angle of incidence is equal to the angle of reflection. So we come and draw our ray to meet the pole at an angle theta to the horizontal, then it is reflected at the same angle, which is theta. I think you realize that each ray has an arrow. Then they all meet at one point, meaning that any two rays you choose to draw, you still get the same position of the image. So as we prepare ourselves for the calculations, we should remember that the more the image goes closer to the mirror, the more it moves away from, the more the image moves away from the mirror and the more it is magnified. So when you bring this object nearer here, this one will shift to a point like this one, and to be magnified. Magnified means increase in size, height, and distance from the from the mirror. So this one you shall see when it is applied when it comes to calculations. But I just wanted you to have it in mind, so that when I talk about it during the calculations, you can easily recall back. Now that has been a concave mirror. What about a convex mirror? So it also has 4 rays. You just choose any 2. They are somehow similar. The difference is that these ones, they don't pass through the focus. They only appear. When it comes to convex mirrors, rays only appear. So you shall say a ray parallel and close to the principal axis is reflected in such a way that it appears to come from the principal focus, capital F. Let's see how that is drawn. So you come and draw the principal axis, then draw the symbol of the curved mirror, then locate the principal focus and the center of curvature. Then they said a ray, we shall put an object, and a ray parallel and close to the principal axis is reflected so that it appears. Appears means when you elongate this, you can call it extrapolating, this one backward, it will appear to come from point F. So let's do that and see. So it appears to come from this point F. Note that this from here, it is a dotted line, and 2, there is no arrow. When you put an arrow, it is never okay, because a dotted line means virtual. The real lines are these ones, this and that. That was ray number 1. What about ray number 2? Ray number 2 says a ray which appears to come from the center of curvature. I think you see the word appears to come from the center of curvature is reflected along its own path. Let's see that. So this ray appears to come from this point C, and therefore it will be reflected along its own path. And because we said as long as we get 2 rays, the intersection is the position of the image. Therefore, this is the top of the image, and it is also dotted because it is got by a apparent intersection of 2 light rays. So this image is called virtual, and it is upright. The one for concave mirror, it was real and inverted. But there are also 2 more rays. Let's look at them. The third one says a ray which appears to come from the principal focus, F, is reflected parallel to the principal axis. So this ray appears to come from the principal focus, therefore to be reflected parallel to the principal axis. That was ray number 3. What about ray number 4? Ray number 4 says a ray striking the pole at an angle theta is reflected, making the same angle theta at the point of the pole. So let's see that. So this ray here will be reflected to make the same angle as the angle of incidence, and when you take it backward, it appears to come from the top of the image. So basically those are the four rays we draw, where we choose from to draw to find the position of the image. Like I said, here we no longer use a graph paper, we only make a sketch. But there's something we need to note. Unlike for concave mirror, when it comes to a convex mirror, no matter where the object is placed along the principal axis, the image formed is virtual, upright, diminished, and between the principal focus and the pole. I think you remember the note we made for concave mirror is that the closer the image is from the mirror to the mirror, the further away, so the closer the object is to the mirror, the further away the image is. But for a convex mirror, irrespective of where the object is, whether close or far away, the image must be between the pole of the mirror and the principal focus. Okay, so now we shall go to what we call a mirror formula. So if F is the focal length of a curved mirror, U is the object distance from the curved mirror, and V is the image distance from the curved mirror, then U, V, and F are related by the expression 1 over F is equal to 1 over U plus 1 over V. This expression is so much used in A-level. So mirror formula, this expression has to be remembered. Also, you need to remember what we noted about the focal length. When it comes to a converging mirror, focal length is positive. But when it comes to a diverging mirror, focal length is negative. When the image is virtual, it means that the distance is negative. And when the image is real, the distance is positive. But you shall see all that. The another formula we need is the relationship between focal length and radius of curvature of curved mirrors. So we know what a radius of curvature is and what a focal length is. So if R is the radius of curvature and F is the focal length of a curved mirror, then R and F are related by the expression R is twice focal length. So always remember that whenever it comes to curved mirrors, radius of curvature must be twice the focal length of that mirror. Real positive sign convention. This helps us to find out what should be negative and what should be positive. So you write and say 1. All distances are measured from the mirror as the origin. That's why we say object distance, distance of the object from the mirror. Image distance, distance of the image from the mirror. Focal length is also measured from position of the principal focus and the mirror. So everything is the mirror is the origin. Then 2, distances of real object and real images are positive. So when it is real, when the object or image is real, it must have a positive sign. What about when it is not? So when the object is virtual or the image is virtual, it should be negative. So you remove this and put a negative. The next is that the focal length of a concave mirror is positive, since it has a real principal focus, while that of a convex mirror is negative, since it has a virtual principal focus. Okay, so now that you have looked at the formula, the mirror formula, and the relationship between radius of curvature and the focal length, and you have also looked at the conversions, what should be negative and what should be positive, we can now go through the calculations. The first one came from UNEP 2008 paper 2 question 1D, and it says a small convex mirror is placed 0.6 meters from the pole and on the axis of a large concave mirror of radius of curvature 2 meters. The position of the convex mirror is such that a real image, note this word, real image, of a distant object, note this word, distance, is formed in the plane of a hole drilled through the concave mirror at its pole. Calculate the radius of curvature of the convex mirror. So some questions, if it involves more than one mirror, it is better you make a sketch. So let's just make a sketch of what is given. But there's something we need to remember, is that rays from a distant object, we saw this word distant, what does it mean? It means that rays from a distant object are always parallel to the principal axis and converge at the principal focus. So for a concave mirror, let's first get we know that radius is 2, therefore focal length will be half this radius to give you 1 meter, which is 100 centimeters. But now we shall consider 1 meter. Then we shall make a sketch. So we have one converging mirror which has where there is a hole drilled at this pole, and a diverging mirror which is here. Now they said rays from a distant object are reflected by this converging mirror. So that will be a ray, it is parallel. And the radius, so it's a wide mirror. So it will converge. It will be reflected to converge at the principal focus. But because there is another mirror, it does not. It is instead reflected again. So in absence of this mirror, this ray would have gone up to this point. But because of the presence of this mirror, this image here, image 1, acts as the object to this second mirror, and therefore to be reflected to be formed at this point. So this is the position of the final image. This is called an intermediate image, and this is the final image. So since we saw that it converges at the principal focus, the distance from here up to here must be equal to the focal length, which is 1 meter. And they told us that the mirrors are separated by a distance 0.6, implying that the balance is 0.4. So 1 minus 0.6 gives 0.4. Now this 0.4 is the object distance of the second mirror. So you come here and say that for this convex mirror or for this diverging mirror, the object distance is this, but because it is virtual, it will be negative. That is why I told you, you must combine sign conventions and the mirror formula and the relationship between radius of curvature and the focal length, for it is the workout questions on curved mirrors so far. So this should be negative. When you forget the negative, everything is not okay. Then the image distance is here, which is 0.6. That means you can get the focal length using the formula. 1 over f is equal to 1 over u plus 1 over v. So u is that, v is that. When I use the calculator, the whole of this gives you negative 5 over 6. But that negative 5 over 6 is equal to 1 over f. Therefore, to get f, it should be the reciprocal of this, which is 6 over 5, negative. To use the calculator, it gives you negative 1.2 meters. Then the radius of curvature is twice the focal length, so it will be 2.4 meters. And that is what they wanted. Then question 2 says a concave mirror of radius of curvature 50 centimeters faces a convex mirror of radius of curvature 40 centimeters and is 60 centimeters from it. If an object is placed midway between the two mirrors, Roman 1, find the position of the final object or the final image formed due to reflection first at the concave mirror followed by convex mirror. Then 2, using a point object, draw a radiogram to show the final image due to the arrangement of the mirrors above. So for a concave mirror, we know the radius of curvature is 50, meaning focal length will be 25. And object distance is half, because they said it was placed midway of the separation. That is why we put a half of 60 to give you 30 centimeters. Then when you use mirror formula and make 1 over v the subject, it becomes 1 over v is equal to 1 over f minus 1 over u. Substitute for f, substitute for u, come up with this, get the reciprocal, and that will be the value of the image distance using the concave mirror. So now that we have known that image of the first mirror, we can go ahead and draw a diagram. So there are two mirrors, then that is the object, by the side reflection is first at the converging mirror, then when the ray reaches the converging mirror, it is reflected and it reaches the diverging mirror. In absence of this mirror, the ray would have gone up to here. So this acts as the intermediate image, which is the object to the second mirror, and therefore it is reflected to form a second image at this point, which is now the final image they want. The separation, they told us it was 60. The object distance is 30. The distance between the first image and the mirror is 150, which is what we had seen here in the calculation. V was equal to 150. That means that the remaining distance, if this is 50 and this is 60, this should be 90 centimeters. Then the final image is V2, image distance is V2, which we don't know, and we have to calculate. So for the convex mirror, U is negative because this is virtual. RI is negative because the diverging mirror. Focal length is negative. Therefore, make 1 over v the subject, you'll come up with negative 7 over 180. Get the reciprocal, you'll come up with negative 25.714. as the distance or the position of the final image, which is here. So the red diagram was already drawn, you don't need to redraw. Then question 3 came from U.A.C.E 2016 paper 2 question 1A Roman 2 and says the plane mirror P in the figure below is adjusted to a position 20 centimeters from the optical pin. The image of the pin in P coincides with its image in M. So this is the plane mirror and this is the curved mirror. Calculate the focal length of the convex mirror. So this one needs you to remember image formation on a plane mirror, that the object distance is equal to the image distance. So let's just make a sketch to easily visualize it. So that is the diagram we are given in the question. So the image, let it be at this point. The image formed, final image formed. So we know that if you look at this, the top part is here and this is also here, meaning they coincide. Image of the plane mirror and image when using the plane mirror and image when using the curved mirror, they coincide, meaning from here to here, if it is 20, even here from here to here must be 20, because for plane mirrors, image distance and object distance are the same. So we shall come and put our 20 there. Okay, then if from here to here, is 40, this is 40, meaning also from here up to here must be 40. Therefore the balance will be 40 minus 30, which is 10. So yeah, it's supposed to be 10. So with respect to the convex mirror, U is 30 and V is negative 10. Negative because it is virtual. So one of our mirror formula is here, meaning that F is negative 15 centimeters. Okay, so that has been how to use mirror formula. What about when they talk about linear magnification or lateral magnification or transverse magnification? So we shall look at the formulae which involve magnification, and then you can go to the second set of calculations. So there are various ways in which linear magnification can be expressed. It can be expressed in terms of heights, or in terms of image distance and object distance, or in terms of focal length and object distance, any. So we shall look at all those 4 cases. The first case comes from the definition, says linear magnification is the ratio of image height to object height, and that is the first expression for linear magnification, that M is equal to H image over H object. So that has been the second case. That has been the first one. The second one can be in terms of object distance and image distance. And in that, when it is in terms of that, we shall say linear magnification is equal to image distance over object distance. Remember, the first one was image height over object height. Now we are dealing with image distance over object distance, and that will be the second formula for magnification. So any of these formulas you choose to apply is okay, because it will give the same answer. Okay, that is case 2. What about case 3? Case 3 is getting magnification in terms of focal length and image distance. So this one needs some little deriving, and let's do it, because if you just quote it, the first 2 we didn't derive because they were also used in O-level, but these next 2 cases are a little new, so we need to derive something here. So we shall come and say that from the mirror formula, which we now know, I want to eliminate, because here I have focal length, which is here, I have image distance, which is here, but there is u, which needs to be eliminated. So what I will do, I'll come and multiply throughout by v each term. When I do that, this by v, I come up with v over f. This by v, I come up with v over u. This by v, I come up with v over v. Now v over v is 1. Therefore, I come up with v over f is equal to v over u plus 1. And I also remember that magnification is equal to v over u, which is here. So I'll come and substitute and make m the subject. So this is the third formula for magnification. What about the fourth formula? The fourth formula is somewhat similar to the third one, only that here we are interested in focal length and object distance. So we shall still do the same procedure, code the mirror formula, and eliminate the image by multiplying throughout by u. So when I do that, I'll come up with u over f, u over u, and u over v. So u over u is 1, which is okay. Then I remember that m is equal to v over u, and here I have u over v, meaning it is the reciprocal. So reciprocal becomes 1 over m. Then make 1 over m the subject, it will give you the fourth formula. So those are the four formulae we shall be using on top of the mirror formula. So I'll remind you that now, the more the object goes closer to the mirror, the more its image moves away from the mirror, and the more it is magnified. So I've brought it back because now it is time to see how to apply it. So now we shall go to question 1. Question 1 came from UNEB 2013, paper 2, question 1C, and says a concave mirror forms an image half the size of the object. That's about magnification. The object is then moved towards the mirror until the image size is 3/4 that of the object. Okay? If the image is moved by the distance of this, calculate the Roman 1, focal length of the mirror, and Roman 2, the new position of the object. So we shall again remember this note that the more the image object goes closer to the mirror, the more its image moves away from the mirror, and the more it is magnified. So with that knowledge, we can come and make a sketch of what can help us to get the focal length and the new position of the object. So there is a mirror. Put the object initially before displacement, and let its distance be u, object distance. Then it forms an image at I1 at a point where this image distance is v, because we don't know it by then. Then they told us that the object is moved towards the mirror. So we shall bring it towards the mirror to a new position O2. And the object distance, we don't know it. It's what they want in Roman 2. But the good thing, the new image is at a point such that the distance between the two images is 0.6. That is why if this is v, this will be v plus 0.6, because the distance from here to here was 0.6. Okay, so with that, we can now go ahead. So before displacement, magnification is a half, they told us, and v1 is v. Therefore, using the expression of magnification in relation to image distance and focal length, it is that Then we can substitute for m and for v1, then make v over f the subject to give you 3 over 2. Okay, that is before displacement. What about after displacement? The new magnification is 3/4 and the image distance is v plus 0.6. Therefore, you shall come and substitute, quote the formula, substitute, split this numerator to give you v over f plus 0.6 over f. But v over f is already known here, so come and substitute it there to come up with that. Now f is the only unknown, so look for ways of making it the subject, and that will be the focal length they wanted. So that is Roman 1. What about Roman 2? Roman 2, they want the new position of the image, this the value of u2. So we know that 1 over m2 is equal to u2 over m over f minus 1. Then we come and substitute. So m2 was 3 over 4, meaning its reciprocal will be 4 over 3. Then f, we have got it as 2.4. Now u2 is the only unknown, so look for ways of making it the subject, and that's what they wanted. Then question 2 came from UNEB 2017 paper 2 question 1b, and it says a concave mirror forms a real image which is 3 times the linear size of the object. There they're talking about magnification. When the object is displaced through a distance y, the real image formed is 4 times the linear size of the object. Okay, if the distance between the two image positions is 20 centimeters, find the focal length of the mirror and the distance y. Okay, so still we shall remind ourselves, and then we draw a red diagram to help us answer the question. So that is the first position of the object. The distance, we don't know it. Then the image formed is at that point. The distance, we don't know it. Then the new position of the object, the distance between them is y. That one it will become, because this is u and this is y, so this becomes u minus y. Then the new image is that, and the new image distance is v plus 20, because from here to here is 20 centimeters. Then with that we can go to the calculations now. Case 1 is before displacement. We have that, then we quote the formula, substitute, and make v over f the subject. What about after displacement? That is what we have. Quote the formula, substitute, split the numerator. Now we have, and we know that v over f is 4. Therefore substitute and make f the subject. So that was Roman 1. Then Roman 2, the distance y, the one this distance. So before displacement, that is what we have, and therefore 1 over m is equal to u over f minus 1. Then substitute and simplify. So u over 20 is 4 over 3, meaning that u is 26.667. After displacement, that is what we have. Therefore quote the formula, substitute, split the numerator. The u over 20 is 4 over 3. Then substitute for u over 20 to remain with y as the only unknown. Then simplify and make y the subject. And that is what they wanted. Question 3 came from UNEP 2007, paper 2, question 1C, and says a concave mirror M of focal length 20 centimeters is placed 90 centimeters in front of a convex mirror N of focal length 12.5 centimeters. An object is placed on the common axis of M and N at a point 25 centimeters in front of M. Roman 1. Determine the distance from N of the image formed by reflection, first in M and then in N. Then Roman 2. Find the magnification of the image formed in Roman 2 above, in Roman 1 above. So for the concave mirror of form M, focal length is that, image object distance is that. Then you can use mirror formula to get the image distance, which is 100. Therefore, we can now come and make our sketch. So that is M, there is N, this is the object, reflection is first at M, so it is reflected, and in absence of this N, it will form an image here. Now we call it an intermediate image because there's a second mirror. Therefore, because of this presence of this mirror, the final image will be here. Okay, so the separation was 90 centimeters, the object distance was 25, and the image distance was 100, meaning this balance is 100 minus 10, which is 10 centimeters. Then the final image, we don't know the image distance. So we shall come and say that for the convex mirror, which is this, focal length is negative, object is negative because it is virtual. So when we use mirror formula, we can get the value of V2, which is 50 centimeters. Then Roman 2, they said find the magnification of the image formed in Roman 1 above. So magnification, remember these are two mirrors, so magnification will be the product of the individual magnifications. So M1 is the magnification of this and this, which is V1 over U1. Then M2 is magnification for the second image using this and this, which is V2 over U2. So V1 is 100, U1 is 25, V2 is 50, U2 is 10. It gives you 20. Now here, you realize that U2 was negative, but I've put a positive. Why? Because it is okay, because we're dealing with magnifications. However, if you want to be consistent and you put a negative here, you will still get a negative 20, which is still correct. So any of the two is okay. If you find it okay to work with negatives, put a negative there. If you don't find it okay, leave it. But here it is a must because it is a sign convention. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on refraction. We have been dealing with reflection. Now next will be refraction at plane surfaces. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.